Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome you to the session on database systems exploiting new hardware platforms. This is going to consist. This session will consist of 4 talks given by distinguished practitioners in the area, all of whom have a slightly different perspective on how we should do this. This happens to be a very important ongoing area, and we will be talking about that. I'll have a couple of preliminary remarks, which gives us a little bit of time for people who are stragglers to come in before the first really substantive talk. So it turns out that the hardware platforms have changed a lot, and our ability to deal with the new platforms is very much in a sort of a catch-up phase. An example, it's in fact very different to have all data in main memory versus having all the data that you happen to have on disk in the main memory cache. That happens to be a very different kind of problem, and in fact, by knowing that data is all in memory, you can in fact make a system substantially faster than it would be by simply putting it all into a main memory cache from a normal disk place. This new hardware setting requires a change in many areas, among them access methods, concurrency, control, and recovery, and you'll see all of those areas discussed today as well as others. The underlying technology on which database systems are built has changed substantially over time. One of the interesting new things is that we have a gap filler technology in the form of flash memory, which in fact has some interesting properties. It's around 10 times the cost of disk storage, but it has the significant advantage of being around a factor of 200 faster in terms of the number of I/O operations per second that it can support. And so both of these technologies are finding a place in modern systems, and both of them are interestingly are moving to a strategy where they don't do any update in place, which fundamentally changes how you want to use them. And in particular, it makes writing to the storage medium very costly indeed. We have memories that are in large servers can go up to 1 terabyte in size, 3 levels of a cache, an L1 cache, which is around a factor of 100 faster than main memory. So how you use cache and whether you use cache effectively is in fact a very big deal in terms of what kind of performance you see. With single core performance seems to be now in the 2 to 3 gigahertz range and not going up. Instead, we're getting more and more servers, and so we have to figure out how we're going to use these additional numbers of servers effectively. And again, that dramatically impacts the way in which you use modern hardware. So this session, we'll talk about that. We'll talk about the problems encountered, the performance of the systems that are result from this, and where we're going to go going forward. I'm happy to report that we have 3 of the real leaders in this area. Paul Larsen from Microsoft Research, Justin Levendusky from Microsoft Research, Thomas Neumann from the Technical University of Munich, and Jignesh Patel from the University of Wisconsin in Madison. And I'm going to now turn the microphone over to Jignesh, who will start the session.
Great. Thank you, everyone, and thank you for giving me the opportunity to present to you on some of the things that we are doing in this space and the big direction change that we need to make as we try to build big data systems that run on modern hardware. So the first is, I'm going to break this up into good news, bad news. The first good news is big data by its definition is about data analysis and management. And database systems are at the heart of it. We at Wisconsin have been screaming loud, databases rule, so it's finally the whole world is paying attention to us. But there is some bad news, which is that the big data software that we deploy today to run these big data systems are largely based on software and technology that were designed for a bygone era. So what we've delivered looks very much like a pig with some lipstick to do these types of processing. And I'm hoping I can convince you why I feel that way. The other good news is there's a lot of growth happening in this area. People are very distracted with this growth, and things are sort of working okay right now. And so they're not quite paying attention to this big mismatch we have between hardware and software. But the last bad news I have for today, after that it's all going to be good news, is that there is a significant mismatch between the hardware and software, and the hardware changes are accelerating in a way that we can't hide in this mode for a lot longer. So what are these hardware changes? This is the familiar I/O hierarchy, where as you go down the spectrum, you pay higher latency. Also, you have higher capacity, but you pay a lot more per byte higher up in the hierarchy. And a couple of disruptions that I want to focus on in this talk. Of course, there are disruptions happening all across this entire ecosystem. I'm going to focus on two. One is at the upper level, which is where we have lots of multiprocessors, things moving towards larger main memory systems. And then down to this area where we now have NVRAM technologies like flash storage that has really brought down the gap between DRAM access and stable storage access by a couple of orders of magnitude. Okay? In the past, what we got across this entire spectrum was every generation, which was about every 2 years, we got processing or storage that was twice as more than the previous generation. So Intel kept giving us processors that are twice as fast for about the same cost with every generation, and they did that for many, many decades. But now what has happened, especially over the last 5 or 6 years, is we've started to see that design of hardware systems across the entire spectrum is governed by power, and we are no longer seeing this high performance, low cost. We are still seeing the double of transistor density doubling as we did before, but even there's been a significant change that the next generation, every generation now has increased from about 2 years to be about 3 years, right? So we are seeing a slowdown even in this very fundamental traditional growth of Moore's law. More interestingly, what's happening if we just look at the processor is that we've hit essentially a power wall, and we are now forced to design processors that have to stay within a certain thermal limit. And so we no longer can keep doubling the performance that we did in the past, but instead what we do is we start having to play around with tricks such as adding more cores. And if you ask architects, there are all kinds of numbers they'll give you. Roughly the answers they'll give you is that we are going to give you about 40% more cores every generation. And they might give us some other hardware mechanisms to do stuff. They're trying to figure out how best to deliver the computing in these transistors that they can put into these processors. Now, data is often growing at a rate that is far faster than this 40% growth every 3 years. And the big problem we have in the database community is as we look ahead, if my data is growing by 40% every year, and this is what Gartner thinks is happening in the big companies, growth of data is about 40 to 60% every year. If I'm only getting 40% more cores every generation, which is now 3 years, I have a fundamental problem. If I've got a data set and I wanted to do the world's simplest operation of just scanning the data set from start to end to do an analysis, I'm building up a deficit of about 2x every generation. Right? Basically what this means is I'm going to need bigger and bigger computers or more and more processors to do the same type of analysis I need to keep up with the data growth rate. And that's clearly unsustainable. So the central message I have today is there are lots of things we could do, including playing with algorithmic tricks and doing approximation. All of that needs to be done. But I want to focus on the fact that we need to do more with less by paying closer attention to what the hardware and software does. I'm going to focus on one very simple operation, the scan operation. I'm just going to scan a data set from start to the end. Maybe I'm scanning it to select some results and feeding it into a machine learning algorithm. Turns out the scan is very, very common. In fact, companies build appliances that are essentially scan-based and keep the data mostly in memory. So it's a very important primitive today. And the way we have solved this problem, at least in this first cut of it, is with this technique called bit weaving. Just presented that at SIGMOD a few weeks ago. And it pays real close attention to this hardware-software synergy. What it's going to do is exploit what we think was a missing dimension in processor hardware today, which is if I look at just a simple operation of adding two 64-bit numbers, really what happens is in a single cycle, at the circuit level, the processor is computing on these 64 bits in parallel to compute the answer to this 64-bit number. So at the circuit level in the processor, there's a 64-way parallelism that we have. The question is, could we exploit that? Processor register words are getting wider and wider. In fact, architects are dabbling around with processor designs in which they could give us kilobit words. And that's fairly easy for them to develop with the technology shift that's happening. So there's at least an order of magnitude today with this intra-cycle parallelism in processors if you view it from the circuit level, and maybe an order of magnitude more beyond that as we go down the future. So I'm not going to tell you a lot of the technical details of what we did, and I encourage you to read the paper or look at the blog post that we have on it. The short introduction I'll do is if you're trying to scan data fast today, you would typically take things that are in relational tables and store that in these things called column stores, so that each of the columns gets stored in a separate file. So if I'm only interested in looking at the quantity field in my query, I'm only looking at that file and not the entire database, which has a lot more stuff in it beyond what I need. And bit weaving works by thinking about the parallelism at the circuit level and exploiting it. It comes in two flavors. One is called bit weaving V, which will actually take each of these columns, we convert that into dictionary compressed codes. So if a column can be represented as 3 bits, we are actually going to scatter those bits across multiple register words. So what you see in yellow is the actual code for a column. It's across 3 consecutive register words. And so the most significant bit of all the codes, if it's a 32-bit example, will be together, and so on and so forth. And we have a whole algebraic framework surrounding bit weaving, which will then let us compute essentially on 32 or 64 tuples at a time in a single processor cycle. So that's what gives us this intra-cycle parallelism exploited at the database level. The other format is bit weaving H, which is a more traditional bit packing format, but it has a couple of additional things. You can read about that in the paper, including the use of an extra bit that we store that makes all the math work, so we can use that extra bit as overflow bit to register whether we have computed the answer. All of this works in a framework in which we can have data stored in either one of these formats. So if I've got a sample TPCH type of query over here, we'll compute a predicate tree. Some of the columns, like ship date, are in bitweaving V format, others in bitweaving H format. All of our math generates these result bit vectors with 1 bit per input, indicating if that corresponding tuple satisfied that predicate. And we can combine all of these things together to produce the final answer. So it's a full framework that lets us answer SQL analytic queries. And the bunch of results that we have in the paper, we do close to an order of magnitude better than the state-of-the-art methods. I want to spend the last few minutes going down in the spectrum a little bit. If you think about how we've been doing computation and in the traditional computing world, we've traditionally taken data that comes from the I/O systems, moved it to various buses to compute answers. And today, what we do is we do sort of the same thing. Maybe we replace things, the hard disks, with flash. But essentially, our processing is moving data through multiple levels of buses before it gets to the processor where it computes. If you think about the long-term implications of storage and computing, the boundary between where you can compute and where you can store is changing. Processors compute fast, but they also store data in caches. Similarly, storage devices store stuff, but they also compute. The cost of storing and actually computing is free. All of the cost is in actually moving and powering these devices. So this is a collaboration between Microsoft and Samsung, where we took one of Samsung's SSDs, which essentially looks like a small computer inside. It's got a lot of processing power. And what we did is we said, if you try to pull data out of the flash device through SAS or PCI or through SATA interfaces, the growth rate of that relative to 2007 is that yellow line. as these vendors try to put more and more capacity in the devices, internally they have got an internal network to pull data from the chips that are on the right-hand side, and that growth rate is shown by the red line, and there's already an order of magnitude difference between those. So he said, can we actually take SQL Server production quality code in a complete prototype? So this is a hacked up version of SQL Server, and we ran TPCH query 6 where we pushed selected computation down into the storage. And if you use just a regular SSD, that's that red box. If you use a smart SSD, that's that round circle over there. The response time is about 2 to 4x better, and the total energy consumed by the entire box is also much better. Okay, so you can start to see where you can generate a lot of these efficiencies of scale. And with that, I'm basically going to end, and I hope I've convinced you that transformative change is happening at all levels. Hardware and software needs to work a lot closely together, and I'd like to thank the Quickstep team that did most of the hard work here. Thank you.
Thank you. So our next speaker will be Justin Levendusky from Microsoft Research, and he's going to be talking about something called the BW tree, which I know a little bit about.
Yeah. Thanks, Dave. Yeah, so I'm Justin from Microsoft Research, and I'll be talking about how to architect access methods for this new hardware era. And this is joint work between David Lomé and Sudipta and Gupta, also at Microsoft Research. So an alternate title for this talk could be the BW tree, a latch-free, log-structured B tree for multi-core machines with large main memories and flash storage. So if you're wondering what BW stands for, it's actually buzzword, because this title is fairly buzzword complete, right? So a good way to introduce the BW tree is to talk about the buzzwords. The first is B tree. So the BW tree is a B tree, an access method or data structure we know and love. And a B tree provides keyword or key range access to records, provides efficient point and range lookups, which is why it's a popular access method in database systems and operating systems. It's self-balancing, and the version we're talking about here is a B-link tree. So in addition to search pointers down the tree, right, we also, each level forms a linked list with each node pointing to its direct sibling to the right. And of course, as an access method, if it runs into memory pressure, we can cache the hot pages of the index in memory and spill over the cold pages essentially to flash or disk. The BW tree starts to differ from more traditional B tree architectures in the following ways, in that we target two main hardware trends. The first is multi-core machines with large main memories. So the BW tree is completely latch or lock-free. The database community uses the word latch, where the rest of the world uses the word lock. So there are no critical sections providing a single thread to get in and update a piece of memory. So worker threads do not set latches for any reason. This means that threads never block in memory. And an important point is that we don't rely on data partitioning to do this, meaning we don't assign updates to a single thread for partition of the index. Any thread can come down and update any page as it sees fit. We also avoid updates in place. So instead, we use delta updates that describe kind of the new change to the page. And this is important because it reduces cache invalidation, which is important for large multi-core machines as well. We also target flash storage. Flash is good at sequential I/O and relatively good at random reads, but relatively bad at random writes due to the flash translation layer that's needed on a random write. So here we use flash as essentially an append log. We implement a novel log-structured storage layer over flash to take advantage, to always write sequentially back to flash storage. So the BW tree is layered in kind of a traditional manner. At the top, we have our key value store interface, the so-called CRUD interface, for creating, reading, updating, and deleting records in the index. We also support, of course, range scans, which of this being a B tree. This layer, of course, provides all the BW tree, the B tree search and update logic, and all the operations are completely latch-free at this level. It assumes everything is in memory. If it needs to bring a page, essentially from log-structured storage from flash to disk, it relies on a cache layer that will do this for it to provide this mapping, which also provides a logical page abstraction for the B tree layer. And below the cache layer, we have our persistent layer, our flash log-structured storage built over flash. And here, it provides sequential writes back to the flash and also provides log-structured garbage collection. Given the main memory tilt for this talk, I'll mainly be discussing for the rest of this talk kind of the in-memory parts of the BW tree, which is the B tree layer and the in-memory version of the cache layer. So the BW tree is rather versatile. If we don't need a kind of a persisted layer, we can use the BW tree as a very efficient in-memory latch-free B tree. And in fact, the BW tree is the ordered index in the Hackathon main memory database system, which Paul will be talking about next. It can also be a high-performance, standalone, persistent key value store. You can think about this as node local storage in a multi-tenant cloud setting, something akin to Google's LevelDB. Or if user transactions are needed, it can also be what we call a data component in a Deuteronomy-style architecture. And Deuteronomy refers to a project we have at MSR to essentially componentize and decouple the transactional functionality in a database kernel into a transactional component, which is in charge of transactional functionality that interacts with a data component, which is in charge of data storage and atomic updates. So the BW tree can support multi-step transactions in this way as well. So now I'll talk a little about how we made the BW tree completely latch-free in memory. And it's been said that an extra layer of indirection helps solve all problems in computer science, and this is certainly true in this case. So all pages in the BW tree are logical. They all have a logical ID, which is an entry into the mapping table which translates its logical ID into some physical location. So if the page is in memory, this can be an in-memory pointer. If the page is currently on flash, it's an offset into our log-structured store. This is important also that the pointers held within B-tree nodes are logical IDs. So any pointers held between nodes on a traversal must first go through the mapping table. Let's read the ID to get the physical location of the page. Right? And this is important for both the latch-free behavior and log structuring. And another important point is that it isolates updates to a single page. So recall that I said we don't update pages in place. This means that it creates a new address on every update to a page. So to avoid having to propagate this address change all the way up to the root of the tree, the mapping table essentially isolates this update to a single page. So to update pages, we use delta records. So say in this case we have the mapping table with our entry P pointing to base page P. So you can think of this as a traditional B-tree page with sorted key vectors, very efficient for search. And so we want to update the page by inserting a record with key 50. We'd first create a new delta record, make it physically point to P, and install it in the mapping table using a compare and swap, which will exchange essentially the old pointer to the base page P now to the delta record. Right? And we can keep on doing this. Say we want to delete a record with key 48. We'd again install it with a compare and swap. And it's important to note here that multiple threads might be racing to update the same page. But the compare and swap, being an atomic instruction, allows only one updater to win, and the rest of the updaters that lose must essentially retry. Right? So it's also important to note here that if we use the persistence layer, log structuring, pages on our log structured store look very similar to how they do in memory. That is, if we flush, say, the base page P at some point to our log structured store, and we add a few deltas, and we need to flush the page again, we only need to flush the deltas back to log structured storage and make them essentially point back to what was flushed previously in the log. Right? And this greatly reduces write amplification back to flash storage. So using delta updates, we eventually can get a very long delta chain prepended to some base page. And long delta chains eventually degrade search performance. Right? So we use delta consolidation. We occasionally consolidate a page by creating a new search optimized page by applying all the delta updates to some page P in this case. And again, install it using a compare and swap. Right? So this now installs a new search optimized page in the mapping table. And this consolidation is piggybacked onto regular operations, as are most other modifications, maintenance modifications in the index. Another important point here is that this being a latch-free data structure, the old version that we swapped out of the mapping table might still be accessed by other threads, right? So to be able to not deallocate the memory before, or to be able to safely deallocate the old version of the page, we have an epic garbage collection mechanism that ensures that no other threads can be accessing that page before we deallocate it. So updates to regular pages are relatively simple. What's hard to make latch-free is allowing the index to both grow and shrink, right? So allowing pages to both split and to merge, right? So I'll describe how splits work in the BW tree. Deletes work in a somewhat similar manner. I'd be happy to talk about it offline. So splits are installed in 2 atomic steps. The first step is to say we want to split page 2 in this example. The first step is to create a new page 4, allocating it in the mapping table, and copying over the upper part of the key range from page 2 to page 4, so the purple and blue records in this case. Right. We then install the split using a split delta onto page 2. And this essentially says that the upper part of the key range for page 2 is now being taken care of by page 4. We make the split live in the index by performing a compare and swap to install the split delta in the mapping table. And at this point, we have a valid search tree, since all searchers coming down through the parent and accessing page 2 will see the split delta and immediately know that the upper part of its key range is now being taken care of by page 4, and they can traverse the side pointer over to page 4. The last part of the split, the next part, is to install the index term at the parent. So this is essentially the new search key and pointer down to page 4. And again, we use an index entry delta to describe this change and install it using a compare and swap. Right? And eventually, all these maintenance deltas are also consolidated into a page, much like the record updates are as well. So I'll finish by just providing a few performance highlights. These experiments are in-memory experiments only, and we compared against the Berkeley DB standalone key value store B tree. We took out user transactions for fairness. And this represents more of a traditional B-tree architecture with page-level latching for updates, as well as updates in place for B-tree pages. And we also compared against a latch-free skip list implementation. So up until the BW tree, latch-free skip lists were one of the state-of-the-art kind of latch-free range indexing methods. We use 3 workloads, one from Xbox, and this is updates, performance trace updating state in a multiplayer online game for Xbox Live. We also used a real enterprise storage deduplication workload from Windows Server, and also a synthetic workload that has a read-write ratio of roughly between the 2 real workloads that we used. So compared to Berkeley DB, the BW tree shows much better throughput performance. And especially of note is the Xbox workload that at any one time updates a really small set of keys, so only focuses on a small set of pages. And here's where we see the latch-free nature of the B tree do very well. So whereas a lot of threads would be lining up behind latches to update a page in Berkeley DB, there are no latches in the BW tree. And we also see some of this better performance is also due to avoiding updates in place for better cache behavior. Versus skip lists, the BW tree is roughly 4x faster and on the synthetic workload. And both indexing methods here are latch-free, right? So where the BW tree really does better is in the L1 and L2 cache behavior, right? So if we look where accesses are going for both indexing structures, the BW tree spends most of its time more in compact B tree pages, searching compact B tree pages, whereas the skip list needs to essentially do pointer traversal on every point of the search as it searches for the next tower down the search. Right. So with that, I'll wrap up the talk, and hopefully I've given you some insight into constructing access methods for these new hardware paradigms.
Thank you, Justin. The next speaker will be Paul Larsen from Microsoft Research, who will tell us something about, I believe, about Hackathon. So for those of you who came here to learn all about that, you won't be disappointed.
Thank you, Dave. Let's see. So, evolving the architecture of our database system. Let's start with a little bit of history. Some of you may remember this. All the major database systems, commercial database systems that are out there were essentially designed in the early 80s. And if you look at what a typical machine looked in the 80s, you'll be astounded. You wouldn't imagine today that you could actually write a database system that could run on a machine like that. But it was done. And all the systems basically have the same architecture. You have data stored on pages on disk. You have a buffer pool, which essentially is a caching layer. We have a lock manager, and so on. In about 2008 and 2009, it became pretty clear to many of us that this architecture wouldn't take us forward. We couldn't continue relying completely on this architecture for the next 20, 30 years. We had to do something. Because here you see the hardware trends. This goes up to around 2009. Memory prices are going down. Intel and AMD keeps on giving us more and more cores, and so on. So what are we going to do? Well, revolution is out. If you're a commercial software vendor, you have to evolve your system. Customers do not want to change their applications. There is no question about it. So the conundrum was, what do we do with SQL Server architecture? How do we move it forward? And I'll talk about briefly mention two projects that we undertook to move this forward. One is Apollo, which integrates column store technology into SQL Server. That started in about 2008. Delivered the first installment of that in SQL 2012, and there are further enhancements in SQL 2014. This particular technology, the issue was not so much the technology. It was well understood how to build column stores. The issue was, how do you integrate it into SQL Server? And we decided to do it, to expose it as a separate index type, which actually worked really well. But that's not what I'm going to talk about. I want to talk about Hackathon, which is our main memory engine, which also is fully integrated into SQL Server. And it is targeted for OLTP workloads. It will ship in SQL 2014. The first beta is available. You can download it and try it out if you want to. And I'll talk a little bit about the architecture and primarily about the considerations in the design. So here is what we call the 4 architectural pillars of Hackathon. Down at the bottom here, we have the hardware trends that you're all familiar with. Declining memory prices, many core processors, and so on. And over there, you have the business drivers, which is really, really important if you are selling software commercially. So first of all, this engine is optimized for main memory. The data structures and so on that we use, everything is optimized for main memory. That's the key assumption. Indices, we support 2 types of indices, hash indices and range indices using the BW tree. They exist only in memory. We do not maintain them on disk or flash at all. There's no buffer pool. There's no caching layer because we assume that these tables all fit completely in memory. Now for durability, of course, we have to put something out on external storage, but all of that is completely stream-based, no random access whatsoever. Because external bandwidth is a lot easier than random access. Given the fact that we are getting many, many more cores, we had to design the thing to achieve very, very high concurrency. So there are 2 things to that. One is we use a multi-version optimistic concurrency control, which I'm going to talk a little bit about. The core engine itself uses only lock-free data structure. There are no locks, latches, or spin locks in sight. That's all good, but individual cores are not really getting any faster. So we had to reduce the number of instructions that we execute per transaction very, very significantly. And the way we do that is we compile T-SQL, which is the standard interface for SQL Server that everybody uses, into machine code. Finally, as a commercial vendor, we cannot, no, how should I put it? The decision was to integrate this into SQL Server because, as I mentioned, customers do not want to change their application. They really do not want to do that. And that's where a lot of the work was. So it integrates both queries and transaction, integrates high availability and backup restore, and so on. All right. Let's talk a little bit about non-blocking execution. One of the issues in SQL Server and in any system that uses locks of various kinds, it's that sometimes those are going to limit the level of concurrency that the system can support. It's fairly common in SQL Server that the limiting factor is not the CPUs, not the disks. It's the latches that you have. You have too much contention on various latches and so on. So what we wanted was highly concurrent execution with full CPU utilization. No thread switching if we can avoid it, no waiting, no spinning, and so on. Just make sure that the CPUs run at full speed because the data is sitting in memory. So that led to three really important design choices. Latch-free data structures only in the core engine, multi-version optimistic concurrency control, and the fact that we allow a limited form of speculative reads. Sometimes we have to allow a transaction to tentatively read something that another transaction has written, even though we're not sure whether it's going to commit or not. So we allow some of that. So what's the result? Well, the absolutely great majority of transactions in Hackathon run up to the final log write. I mean, we've got to write the log so we don't lose things without ever blocking or waiting. They just run straight through, write to the log, and then wait for the log write to finish. The in-memory organization of the data is quite straightforward. It's a multi-versioning system, so we have timestamps to indicate the valid time of a version. We use embedded pointers, so indices use embedded pointers, so we can always refer directly by a physical pointer to a version. Two index types are supported, hash indices, and range indices using BW trees. I should point out that we do not rely on partitioning. Any thread can at any time try to update a record or access any record. Okay, so why multi-version optimistic concurrency control? This may be obvious to many of you, but perhaps not everybody. First of all, multi-versioning, readers don't block writers, and vice versa. Essentially, we separate out the readers. They don't compete with themselves or with writers, and then the writers just have to compete with other writers. No lock manager. Lock managers add huge overhead, especially in the main memory setting. It was just not acceptable to have that high overhead that you would have to take out the lock for every record access. It's actually more expensive to take out the lock than to access the record. Well, you can get around that a little bit, but in any case, no deadlocks, so we don't need any deadlock detection. It can be made highly parallel. In the implementation that we have of this optimistic multi-versioning, there is only one synchronization point, and that is each transaction has to take out an end timestamp, and those have to be sequentially ordered. That's one single atomic instruction. Everything else happens in parallel. Lower isolation levels run very, very fast. The end result is that this performs very well even under high contention and handles long read-only transactions well. There you see an example of the kind of scalability improvements that we see compared with locking. Much, much higher scalability. A little bit about where Hackathon fits into SQL Server. First of all, Hackathon itself is just a storage engine, compiler, an in-memory storage engine, a compiler that compiles T-SQL into native code, and then a lot of supporting runtime routines. But it relies on, it leverages a lot of the features in SQL Server. For example, it doesn't have a catalog. It uses the standard SQL Server catalog, and it gets its metadata from there. High availability is integrated with a SQL Server's high availability story. Doesn't have a separate log. It uses the SQL Server log and so on. What actually took most of the work are those arrows here, the integration with SQL Server, not the Hackathon engine itself. As I mentioned, transactions and queries are fully integrated with SQL Server, so you can access it using regular SQL Server queries. You can, in a single query, you can access Hackathon tables and regular SQL Server tables. Updates can go across multiple tables, and so on. This is absolutely crucial from a commercial point of view and from customers' point of view. Here you see some idea about how much throughput improvement we can get. This was a workload where SQL Server had a lot of contention. And what we did was we converted the key table there to an in-memory table without changing any other code at all. That got us a 3.3x higher throughput in this particular example. Then there was a stored procedure that did the work. We converted that to a native stored procedure, and that got us a throughput improvement of almost 16x. So a number of customers are running this, some in production, some in test. bwin has been running it in production now for quite a while. And their throughput maxed out at 15,000 requests per second using SQL Server, and throwing hardware at it didn't help. Partitioning did help a little bit, but not enough. So with the Hackathon engine, they got that up to 250,000 requests per second, which was more than enough for them. They have other bottlenecks that they hit much earlier than that. EdgeNet is another company where their problem was data ingestion rate. They need to ingest data daily very, very fast. They maxed out at 7,500 rows per second, and with Hackathon up to 126,000, which allowed them to change their business model. Instead of batch ingestion, they can do it essentially online. That's all I had. It's available. You can download the beta and try it out if you want to. It will ship in SQL Server late this year.
Thank you very much, Paul. Our final speaker for the session is Thomas Neumann from the Technical University of Munich. And Thomas will tell us about the hypersystem.
Yeah.
Oh, and one more thing is we will open it to questions after Thomas's talk.
So today I will talk about the hypersystem, so a research database system that we built at our university. And the main goal of the system is to build a combined engine for OLTP and OLAP processing, which is something that traditional systems don't usually do. So if you look at the two different kinds of workloads, you see in an OLTP setting where you have very large number of relative simple transactions, like users orders products, or user buys something, or users make phone calls. Relative simple transactions, but they have a very, very high rate. where we mainly care about updates performance. And on the other end of the spectrum, you see the OLAP processing. We might have much fewer transactions, but they aggregate and look at very large volumes of data. And these are quite different application scenarios. In particular, they are conflicting. Now if we want to do both, so for example, you want to analyze our current business data, we have the problem that this very high update rate conflicts with our analytical queries because, of course, the data must not change for the OLAP transactions. Yeah, and traditionally, database systems are not very good at doing both. So they concentrate on one of the two things. So standard things like 2PL locking would not work here. But if we assume that our data is in main memory, then we can suddenly do things we could not do before. Yeah? So then we have new options. And in fact, this was in a way the founding idea of our project. So we said, okay, if we have data in memory, we can use this fact for transaction isolation. So how does this work in a very high level overview? We have one process who owns the data, and all the updates, the short updates, are running against this big chunk of data, and we execute this as quickly as possible. And now, if we need a stable state of the data for longer time, so for a long-running transaction, what we do is we copy the database, of course, only conceptually. Yeah, physically, you cannot copy a multi-gigabyte of data. Conceptually, we copy the database by forking our process. We make a virtual copy of this thing. And what happens then is that these virtual copies are initially the same physically. Yeah, but once you perform updates, the analytical transaction is not allowed to see. This update is captured by the memory management unit. So you get a trap. Then you do a copy on write mechanism, so you replicate the changed data, and then these two are perfectly isolated. And the good thing about this is that this is very, very cheap. Yeah, because we get the checking for the rights to shared data by hardware support, so very little overhead. And this allows us to execute both an OLTP and OLAP concurrently with very little overhead. It means there's a tiny bit of overhead. We see some numbers, but it's very little. Okay, so this was in a way the original idea. And now when we built the system, we noticed some more things. In particular, we noticed that the traditional way to execute queries, Paul has also mentioned this, is not so very good. Here, like the classical iterator model where you interpret operator trees. This is fine if you wait for disk here, because disk is so slow, it doesn't matter what you do in your operators. But if your data is in memory, then suddenly this is expensive. Here also the code itself is not very nice. You have many branches, you have a lot of function calls. This is not so nice on a in-memory execution. So what we do instead is we also compile queries, and we try to compile the queries in a way that we touch data as rarely as possible. So in a way, we think about like memory access is an I/O operation. This is an exaggeration. Sometimes you simply have to go to memory. But the idea is that we don't want to access memory if we don't have to. Yeah? So we try to minimize accesses. And also what we try to do is we try to get tight loops over small pieces of code, because this behaves more nicely in your branch prediction in your CPU. So you want to perform a large number of operations in a tight loop. Now, this whole execution model is in particular important if you run OLAP queries, because there you aggregate millions of tuples, so you really care about. But also in the OLTP side, which is not that dependent here, you notice the differences in the execution model. Okay, now how does this work in a one-slide summary? So what we basically do is we take our query, so here is shown like a small algebra tree. We take our query and then we analyze the query to figure out what are the pipelining fragments of the query. So pipelining means where can we pass data between operators without materializing. For example, if this is here in a hash join on top, you assume we have a scan. This will load materialized data, of course. Then we perform some in-memory operation, for example, the selection, and then we materialize into the hash table of the hash join. So the idea is that in every pipeline fragment, you always load the data into your CPU registers, and ideally, really your registers, if you can. It's not always possible. If you can, you do this. Then you perform in CPU, whatever you want to do, and then you materialize into the next pipeline breaker. And this is about the minimal number of memory access that you can do, yeah? Because by definition, you must materialize at this point. So this is conceptually very nice. And now if you combine this with an efficient way to generate machine code, and we use the LLVM toolkit to do this, then we get extremely compact and efficient code. In fact, we are currently close to, and always humans are always very smart, but we are close to matching performance of handwritten code for very large classes of queries. So this is very nice. Now, if we look now, go back again a bit from the OLAP side and go look to the OLTP side, we notice that the OLTP performance is very much dominated by index accesses. So index accesses is an absolute most impact on the performance of OLTP processing. And the question is, what should we do? Yeah, if you look at what we teach to our students in introductory courses, how do we index data in memory, the classical things we teach are hash tables and trees, in worst case even binary trees. And we see these both have pros and cons. Hash tables, of course, are nice because if you are lucky, you need one access and you get your data. Very good. Not guaranteed that you need one, but should be. Downside is, first, you cannot do range queries, clearly by definition. But it has also some other very unpleasant properties. Hash tables don't very well if you have non-unique keys. With duplicates, you have problems updating your index. And hash tables are an absolute nightmare to grow. I mean, there are hash tables that can grow, but you pay a heavy price for this. Growing hash tables is not a very good operation. So therefore, we don't like them. If you look at trees are feature-wise good, of course. You can do range queries or good things, but trees are slow. Binary trees are terribly slow. B trees are not terribly slow, but also they are not perfect in performance. In particular, since if you look at what happens if you navigate this tree, what you always do is you compare two elements and then you branch depending on the comparison. Yeah, clearly. But this is not so good because you cannot predict this very well in your CPU. So this is a relatively slow operation. I mean, not terribly slow, but relatively slow. We therefore, at least by default, use a different kind of index structure, namely a radix tree. So a radix tree, that's a small example shown to the right, uses at every level of the tree 1 byte of your index key to navigate to the next child. So you don't compare, but conceptually at least, you have one big array which tells you if you have this byte value, I go to this node. Conceptually, you don't implement it like this, but conceptually you have this. So you have direct access, a bit similar to a hash table, but of course only for 1 byte. But you directly jump, you don't compare. This is good and fast. Problem is, if you use a naive implementation of a radix tree, you have a problem with space utilization. These things can get very large. And if you're not careful, you can also get very deep, because you have to index your key. So if your key is long, this could be very unpleasant. But fortunately, both of these problems can be solved. And in fact, we use a radix index by default. And here I try to give, I have a limited time here, but I try to show you that at least high-level ideas how you can make a radix tree practical. So basically what we do is we say, okay, this space problem is because your domain is utilized heavily in some parts and underutilized in other parts. And how can we solve this? We can solve this by using different types of nodes. So here I've shown you the 4 types of nodes we've implemented. So depending on how many child nodes, you use more widely or more wide or more narrow nodes. So, for example, you have one node type if you have only 4 child nodes to one node where you have 256 child nodes. So this varies. You adapt to your data distribution. And the nodes are made so that you can find the right neighbor without comparison. So this is graphed like this. And then you get both the direct access behavior and still compact representation. Now, to make this really practical, you have to do some more tricks. You have written like here with path compression and lazy expansion. So in particular, you try to avoid generating nodes that don't carry information. So if they don't help you to distinguish child nodes, don't store it. So skip everything that you don't need. And if you do this, you can get a fixed, an upper bound on space utilization per entry, which you usually don't have. A classical radix tree is bound by key lengths and not by number of entries. But here you can implement it in a good way. So this behaves quite nice. Now, one final implementation thing I want to mention is that if you look at the database system, you realize your database system in general can be huge, very large, but in practice, the set of data you really access is relatively small. The working set is not so large most of the time. You're accessing a small number of tuples that you really update. Now, unfortunately, these tuples are not necessarily close to each other in a physical sense. Yeah, but you would like to have them close for several reasons. For example, for our copy and write, it's important, but in general, you might want to store your read mostly data more aggressively. Yeah, like you compress, or in extreme case, even move it to disk. Yeah, so you want to store it differently. And therefore, we in our storage scheme use such a hot-cold partitioning, or should perhaps say more as a cooling partitioning. So on the top, you see the hot items, means items that are accessed all the time. These are stored just as they are, so on a classical in-memory pages. On the lower end, you have the frozen page data items that have not changed for a long time. So therefore, most likely never change. Yeah, most of the data that's old will never change. And we can store them differently, like we can compress them, put them on huge pages, and so on. And then we move tuples up and down in this hierarchy based upon observed access patterns. So we trap accesses to the pages in between, and then we decide if we can go up and down. Now, as I said, we built in a combined system, and traditionally people said this is not feasible, at least not with good performance. So what kind of performance can you expect? Here are some numbers from a very small server machine. And so we see on a really more like a desktop, on a very small server, we can see something like 138,000 TPCC transactions, so OLTP transactions per second, which is a very, very good number. So on a single core. So this is very fast. And if you look at the OLAP processing, here you see TPCH, scale factor 10. If you execute all queries sequentially, single core again, we need something like 14 seconds, also very fast. Now, but the most interesting number actually is the third one, namely what happens if we do both. So we run TPCC, and simultaneously we run the TPCH queries adapted to the C schema, so we do both on the same data set at the same time. And we see if we do this, we get some 122,000 transactions per second, slightly less than without queries, but not terribly much less. And the OLAP part is nearly unaffected. I mean, we have some overhead to copy and write, but in general, we get extremely good performance, both OLTP and OLAP and both. So to conclude, I hope I've shown you that main memory is more than a fast disk. Here in memory, you can do things you cannot do on a disk. Random access, but also here what we use is memory management using this. And not only can we do this, we should do this, of course. Yeah, we should, for example, use different indexing techniques. Our index would not be that great for a disk-based system, for example. Yeah, so this is aimed for in-memory, and also our execution model is made for in-memory processing. And the system that we have built actually demonstrates in a practical sense that you can get very decent behavior in both OLTP and OLAP. And this in a really full-fledged system. So we do AC transactions, we offer you SQL support, we don't require partitioning or this kind of things. So we get a very reasonable system. And in fact, you can at least soon, hopefully, try this out yourself if you want. So thanks.
Thank you very much, Thomas. So before this session, over the last couple of weeks, I've been interacting with the speakers, and I've been emphasizing that they should not exceed their 15-minute budget. I must congratulate them all. They came through with flying colors. So that leaves us with 15 minutes for question answering. So what I'd like to do is to sort of just remind you that there is a person in the back of the room wearing a red shirt, carrying a microphone. And if you're interested in asking a question so that we can get the recording correctly, we would ask that you ask it through the microphone that our helper here is providing. Also, if you have a particular person in mind that you want to ask the question of, please indicate that too. Otherwise, I'll open it for everybody.
Compression, we have to worry about compaction, and there the issue is between, we want to try to run registers as much as possible, and even memory is really, really slow for us. And so it might be interesting in bit weaving and techniques like that too are things that we have to do because
might be an interesting exercise to compare. There are very big differences. So you have transactions, we don't have transactions. You have OLTP versus, but we also have to update the routing tables while we do this. But it's glorious to see a lot of resonances with you.
You want to say anything, Thomas?
Of course, you're right. So otherwise, I cannot say much about this. Yeah, I mean, the problem we see here is clearly true for everybody who has to process large volumes of data quickly. The only thing is, traditionally, database systems did not do this because if you wait for disk, you have a lot of time for your CPU. Yeah, but of course, you're right.
And there's some interesting parallels where people sometimes in the networking world, from what I understand, you will sometimes burn some of your logic into FPGAs and put it really close. And I think the database community is also starting to explore some of that for specific processing now. So there's a lot of parallel there.
That's great stuff.
Next question.
So I was interested to know your opinion about the use of GPUs and the CPU-GPU combined, which is appearing into various machines, and how it's going to affect not only the OLTP workloads, but also the OLAP and OLTP combined that you were discussing.
So I can take that. I think we are very excited by, especially with what's happening with integrating GPUs and CPUs on the same memory bus. And effectively, it gives you a massive parallelism. I worry excessively about the joules per cycle that I can extract out. And that's looking very good for the GPU compared to where the CPU cycles are going, especially the non-risk cycles are very expensive. The interesting part is, can we build a lot of the problems going forward, at least from the analytics side, is getting data into the processor. So memory buses are not scaling as fast as the rest of the ecosystem scaling. And if we can get that memory architecture going and scaling out on a 10-year horizon, that would be great. It's not there yet, and I think there's considerable work to be done in terms of whether we can feed the beast at the speed at which we can consume it. Nice thing about databases, we can go and adapt our computation like we did, for example, with bitweaving. We can change kernels, there are just a handful of them, to work at the speed of the hardware, but it's also the rest of the ecosystem, and the bus is where the next set of problems is after we make the algorithmic changes that are needed.
So I have a general comment on that. One of the problems with using special hardware, and it's indeed sort of a universal problem with respect to things like the partitioning approach to doing databases, which is sometimes you're trading sort of micro performance for organization and staging and managing your data in such a way that you can actually exploit these resources. So the real problem for these things, I think, is being able to figure out a way where those sort of techniques can get integrated smoothly without enormous overhead, because if you don't do it right, then you lose more by simply staging it incorrectly than you do gain by it.
So Alex Salai, Johns Hopkins. And so much of the discussion today revolved around in-memory databases. And it reminded me of an old paper Jim Gray wrote about 25 years ago called the 5-minute rule, where he claimed, or where he stated that essentially a business argument can be made for in-memory databases, that how much memory should we buy to actually basically make up for the IOPS of hard disks at the same price. And then he claimed this crossover time was 5 minutes. Then Gus Grafer redid it then a few years later, where he claimed when flash showed up it was 15 minutes, but the economics have changed. So I have redone this recently just for my own amusement, and we are back at 5 minutes, and the memory that basically takes up 5 minutes of IOPS at around 900,000 IOPS per machine is about 600-700 gigabytes, which is very much in line with the run-of-the-mill server these days, or sort of at the top of the line.
So I could comment, or I could ask some of the panelists to comment. So one of the things that is pointed out, I think, by Jignesh and by Thomas as well, is that you can do things in a fundamentally different way if you know that everything is in main memory. Whereas most of the 5-minute rule type of stuff was predicated on the fact that you were using a traditional architecture. And so I think the game has changed. And one of the you get enormous gains by knowing that the data is in main memory. So I'm not sure that the 5-minute rule continues to apply in such a strong way.
I think the other part is communication is where a lot of the bottleneck is, not just buses in the system, but people increasingly deploy these massively distributed systems. And it's not just for the Googles and the Facebook of the world. You're forced to do that even at a much smaller scale. And again, it's that networking speed. We are at 10 gig Ethernet right now. It's not changing as fast as we can densely pack storage and compute in single silica, right? You can today build system on a chip. You have those in your phones, in your pockets today. And you can pack incredible amount of storage compute together. But getting that in and out is a huge problem. In fact, this is what the quantum computing guys worry about too a lot. They can do a lot of stuff inside a quantum bit, but communicating with the outside world is where all the challenges are. And I think that's the longer term perspective, is how are we going to build systems where we excessively pay attention to communication, which traditionally we haven't done in the database world, is very important.
Yeah, but even in this world, the IOPS, that how we can page things in and out or from one system to another, will be important as long as we will continue to have data sets which are larger than a contiguous memory of a single system.
But I think there's another dimension that we haven't looked at. We always do replication for fault tolerance. We haven't fully exploited the equations between high availability mechanisms you use for that, performance-related things about which replicas to use. I think there's a huge field ahead of us if we start putting all of that together in cost-effective ways and balance not just performance, but these other aspects that people worry about in a single framework.
Paul would like to comment.
Yes, it's clear that it's more cost-efficient to move some of your cold data out on cheaper storage, whatever storage form that has. But what is not so clear exactly how to organize that, because you still want to have very rapid access to it and integrated access to it and so on. So that whole issue of how to integrate cold storage management into it is an active area of research right now. And the solutions are not clear. There are probably going to be multiple solutions. But we'll see how it works out over the next few years.
Yeah. So just like to point out that Thomas talked about one approach, and we actually redid the 5-minute real calculation for one of our Paul and I did for work that recently appeared in ICDE, and found roughly the same numbers as you did. And this is an active, as Paul said, an active area of research in the database community, and all the major systems projects have it. HStore, Hyper, and Hackathon as well.
There is one thing that happens when you store data on the secondary storage device, which changes things and perhaps substantially. You tend to have to go to an async programming model where in fact now threads can wait and things can block and more things can be active at the same time. And this is sort of the complexities that you avoid by strictly a main memory approach. But what people are, as we indicated here, people are in fact looking at this, and so maybe the best comment to say is to stay tuned.
So what is the mechanism typically used in the memory database for persistency and for tolerance? So you mentioned you use duplication. Is this a typical way to do that, or you use some fast secondary storage to maintain the persistency and for tolerance?
Well, I can say how we do it in Hackathon. To guarantee sort of persistence on a single machine, we use logging, traditional logging. We write out a log. And then we have a novel checkpointing scheme to speed up recovery. But it's also integrated fully with SQL Server's high availability, but it basically maintains multiple secondary copies, and any one of those can take over if the main fails. So those are basically the approaches that are currently being used.
So for the logging mechanism, so are you logging into the secondary disk, or you're logging in the memory? So if the node got failure, so what happens?
No, we are logging. We do logging to guarantee persistence of the data, because we can lose the memory image at any point in time, which means that we have to log to some kind of persistent medium. Which today would probably be flash, because we need the rates that flash can provide.
And there are other options. There are products out there that will do case safety, where in an in-memory transaction, they will send that update to K other sites, and it'll be in memory. And so you can run numbers and calculate how much, what the risk is of losing the data. People are playing around with battery-backed RAM for fast log storage in startups in the Bay Area for problems like this. But the thing I want to mention is just not main memory, right? I think the fundamental hardware is changing in such a way. We focused a lot on main memory systems over here, but you can start to envision systems which maybe if you're doing analytic workloads, for example, in bitweaving, we really don't need a main memory system for that type of stuff. I just need processing coming out at the speed at which the bus can deliver. And maybe that is sitting inside a flash storage, and my future appliance looks like slow spinning hard disks, lots of them being able to feed the processing thing at scale, or flash storage that just feeds directly into the processor. It may not be a high memory system, right? I think we care about joules per query and a sustainable 10-year path to keep up with the data growth rate. And there may be very different architectures than what we see today. So it's very interesting to explore that appliance design with that goal in mind.
There is a community, more or less consensus of building replicas for high availability as opposed to doing fast recovery. And there are a number of techniques that people use. The details are different, but most of it involves replicating the log and shipping the log and having re-executed on secondaries, one form or another.
Hi, Arnab from Ohio State. So I wanted to touch upon something that Jignesh just mentioned as well. So, and actually most of the architecture so far that we've been talking about is main memory followed up by SSDs as a trend. I like to spend some time trying to envision what I can buy on Newegg for, a dream system of mine. And the latest configuration that I built was $25,000 for a terabyte of memory across, I think, 3 machines. Which is fairly commodity, and the fact that you can actually do this on a single credit card if you wanted to is kind of cool. And so
you have a very good credit rating.
Sure.
Dave is looking at his credit card; he's already maxed it out.
What's that number again?
So the way I see it is that if we're reaching this level of commodity where we can buy hardware at this level, distributed query execution becomes an interesting possibility. There are log-free data structures that we're talking about. So how about thinking beyond and just one core or one node, sorry, and then going beyond that. And I understand that Ethernet might not be the solution to this. So there might be some other hardware requirements. Maybe throw in some InfiniBand, which is a few $100s, but it does get us to the terabyte of memory threshold. Which is, I think, a good significant.
I think the key part is commoditization of that high-performance hardware, the networking level, which is getting there, not quite there. In fact, for stuff like you're saying, you don't even need to buy the machines. You can go and rent high instances on Amazon, and the networking may be a little bit slower, a lot slower, but you can get. If you wanted single box, high memory instances, you can pay as you go, right? Amortize that.
The reason was essentially multi-node. So multi-node, reaching that level of memory especially EC2, the variability is crazy enough that...
Franklin's smiling there because I think he doesn't buy hardware anymore. He just rents it out on EC2.
I mean, I would not like to, but the network variability on cloud right now is something that I cannot guarantee, especially if there is just Ethernet and 10 gig.
No, and I worked for Teradata for 2 years. They make a lot of money by selling really essentially what is a fast hardware interconnect with commodity processors.
How come that's the only...
So Thomas Neumann has wanted to comment.
Sure.
Yeah, I want to mention what you should realize is that you can get the terabyte on a single machine for nearly the same price. And it's not much more expensive. And of course, depends on what you do. If you're just running an analytical query, scale out is not an issue. If you're running OLTP, scale out is an extreme pain. And you can think about how many people have more than a terabyte of active OLTP data. Not many, I would guess. So it could be, for example, we looked at this. What we looked at was concentrating the updates on one node and then scaling out to different nodes for query processing. Right. This makes perfect sense. But you try to centralize your OLTP transactions because distributed transactions are an absolute pain. Yeah,
Thomas makes a really good point, which is that what happens in systems is you end up partitioning them if you have to scale them over multiple machines. And the more you can run on a single machine, the less hardship you incur by doing partitioning.
Commercially, this is definitely the way it's going, that you offload a lot of the read workload onto secondary copies, and you had the update activity on your primary node. That's a lot easier than actually trying to distribute update workload across OLTP update workloads across a cluster of machines. It is a royal pain.
I buy that.
So actually, I want to push back on running everything on a single machine. The problem there is that the memory becomes larger and larger, and the memory bus actually is not increasing at the same speed. So if you look at the numbers, if you have, you have 500 gigabytes, just scanning that memory, it will take 10 seconds. So if you want something very fast, again, it will depend on your computation. You'll be better off actually to distribute this 500 gigabytes, say on 10 machines, 50 gigabytes on each.
Sorry, can I interrupt you? We agree with you completely if we are talking about OLAP and analytical workloads, because those can be distributed. We were talking about OLTP workloads. Those are really a royal pain to distribute across multiple machines. Okay. So OLAP, we're fine. We agree with you.
Okay.
We have one more question back there, which I think will have to be the last one because we're already a bit over time.
I can also sit down. But so Intel's Haswell supports hardware transactional memory now, and it will be available hopefully soon, not soon enough, in server sizes that are interesting to people in this room. So there was a whole lot of interesting software transactional memory style thinking in the BW tree we just heard about. So does HTM make you say, rats, I wasted a lot of work and I'm going to have to throw it all out? Does it make you say, heck yeah, I did something that's going to be better than what HTM can do anyway? Or does it make you say, ooh, I think we've already laid the right foundation for taking advantage of that, and that's going to make us even better?
B.
Well yeah, B. The answer is, I mean, we've looked at hardware transactional memory and essentially porting the BW tree to transactional memory. Certainly, creating these types of data structures gets much easier conceptually, right, if you have that crutch. We'll have to see how well it performs. I mean,
from a commercial point of view, there are issues. First of all, we don't know how well Intel's hardware transactional memory actually works. We just don't know. We'll have to see. The other part is, well, unfortunately, the world is not going to running Haswell machines, Haswell sockets everywhere. There's going to be lots of machines for a long, long time that don't have hardware transactional memory, and our software got to run on all those machines as well. Third thing is, does it give us sufficient gain compared, for example, with the log-free data structures that we're using in Hackathon, that it's worthwhile doing it or not? And we don't know any of that yet. So we'll have to see.
So I think we're going to have to wrap up now. I want to thank you all for attending, and I want to particularly thank the speakers today who did a fine job in exploring what is in fact a very large space of database systems on new hardware. Thank you all.